So let's review 4.4, I call this B, number 67 and 68. So, it's probably easier if I open up the book, actually. It'd be easier if I just had the book here, because there's a picture, and I want to draw on the picture what we're doing here. Let me see if I can get that textbook pages open here. Page 293. 293. Okay. 293. So glad this book has the correct page numbers for everything. So let me show you here. So here we are, page 293. There we go. So we have for 67, here's 67, the graph for 67. And let me see if I can put this into my whiteboard program. Oh, look at that. Wonderful. Let's go back to this whiteboard program. Much better. Here we go. So here's page 293. Here is number 67. Yeah, okay, good. So what we're doing here is we are using the accumulation function. So here we have our accumulation function. Right? Here is saying that g of x is the accumulation function, the integral from 0 to x of this f of t function. This graph is the f of t function here. This graph is f of t. And g of x is accumulating the integral from 0, starting at 0, to some value along the equation of f of t. And so we want to estimate the value of f of g of 0, 2, 4, 6, and 8. 2, 4, 6, and 8. So we want to estimate the values of g of 0, g of 2, g of 4, g of 6, and g of 8. So we're going to look at the area under the curve, is basically what we're asked to do. Find the area under the curve, estimate our graph here. We have a kind of flat line, and then we have a kind of curve, and then it looks like a linear part right here. This is kind of a piecewise equation going through these things here. So we're going to look at those answers and see what we can determine about this g equation, what the values of g are, and how this graph of g is going to look. Because eventually we're going to have to sketch a graph of g, what it roughly looks like. So let's look at part A. Let's look at, let me do this in black, g of 0. So again, what we talked about was this integral is the accumulation, right? We are accumulating all of the values here. So we're starting at 0 and going to 0. So what's g of 0 going to be, everybody? We talked about this yesterday. When we have our integral, basically what we're saying is that g of 0 is the integral from 0 to 0 of f of t dt. And what's that going to equal? What's the integral from 0 to 0, right? Here we're plugging in the 0, right? Here we're plugging in 0. So what is the integral from 0 to 0, everybody? If we did an integral from one number to the same number, what did that make for us? Well, that was 0, wasn't it? We went nowhere. If we're looking at our accumulation, our integral creates an area, right? When I say integral, you say area under the curve. So if we start at 0 and we go to 0, we have accumulated nothing. We are staying at the same place. We have not moved at all. And so we have gained no ground. We have gained no amount of anything. So the integral of 0 to 0, or the g function, this accumulation function, we accumulate starting at 0, we start at nothing. So that's a value, right? This is a point. We can consider this an x and this a y. That's like our x point, that's like our y point. So the first coordinate of our function is 0, 0. So we can keep this in our minds and think about, well, we're looking at a graph of g. We have one point, we can kind of think about what the function is going to do. So let's look at g of 2. Again, we're doing the integral from 0 to 2 now of f of t dt. What do we think this is going to be? Integral from 0 to 2. So here's 0, here's 2. So what we're looking for is all of this area here. This area here is the integral from 0 to 2 of f of t, right? The integral from 0 to 2. So how much is this? Let me erase this. Let me figure out how much this is. We can see the squares here. Best way to do this is to look at the squares, right? We have all of this from here to 2 of these squares here. So I've got 1, 2, 3, 4, 5, 6, and maybe these two together make a half. So maybe it's like 6.5, approximately. Right? You're kind of estimating here. 1, 2, 3, 4, 5, 6 whole values, and then like these two maybe make a little bit, maybe a half, maybe a whole, maybe, well, because it's like a little curved here. It's not quite. This is not quite a half. Maybe it's like 6.75. Let's say 6.75. 6 3/4. Might be a little more, might be a little less. Approximately 6 1/4. 6 3/4. So again, we have another coordinate for our graph of g. 2, 6.75. Our graph has risen from nothing, from starting at 0. It has grown to 6.75. So our graph of g has increased, right? Increased from 0 to 6.75. Because we are accumulating more stuff. We are growing our stuff. So let's look at g of 4. From integral from 0 to 4 of f of t dt. So now we want the integral from 0 to 4. So from 0 to 4, we're going to look at from here to here. All of this area in there. So we count the squares. Right? We have all this area. There's really no, we could do a Riemann sum, but we don't really have the values. Let's just count the squares. 1, 2, 3, 4, 5, 6, 7. I'm going to call this 8. And that's still our 0.75. So maybe make it 8.75. Yeah? 8.75. Approximately. So here's another coordinate we have for our g graph. 4, 8.75. And if you wanted to do 1, you could do that too. If you wanted to find more values, you could just find like 1, 2, 3. You could find all the values. If you want to find value of 1, we're here, right? This function here is just 1, 2, 3, 4. So 1, 4. We know that that's a value, 1, 4. We can look at that one. All right, so that's g of 4. Let's look at g of 6 and g of 8. Two more. G of 6. Integral from 0 to 6 of f of t dt. So from 0 to 6, we want to go from here to 4, 5, 6 here. So we have all of this area on the top and the bottom. Emmanuel, welcome back. How's your arm? Feeling good? Oh yeah, well, you know, this is your first, yeah? Number 1? Manuel got his COVID shot, everybody. Round of applause for Manuel. COVID shots for everybody. My wife had her first. She had a little fever afterwards, so we'll see how you feel tomorrow. Now you're going to get tracked, but Bill Gates is going to track you. Of course, not his wife, though. They're getting a divorce now. Did you hear all about that? That's, I don't know. It's going to be interesting. Anyway, good job, Manuel. Keep it going. Everyone else, you're next. Get your jabs, everybody. Get your jabs. Anyway, we're talking about the area here. We're talking 67. Looking at the values of this accumulation function g, right? How is g growing or shrinking as we travel along this f graph, as we accumulate more and more stuff? So we've gained up to 4. We've got 8.75, right? Now, this area below the curve that we start accumulating, this area, we start accumulating some negative area, everybody. Here, this is going to subtract from our value of g, right? When the graph is below the line, that's when the function is decreasing, right? That's when the function is reducing in value, right? So if this is shrinking, I have all of this positive area, which up to 4 was 8.75. Approximately all this area in here is 8.75. We just counted the squares. 1, 2, 3, 4, 5, 6, 7, 8.75 approximately. And now we're going to take away some of this stuff. We're taking away, this is probably at least another 1, right? This area in here, this is probably at least 1 whole. Well, this looks exactly like 1 whole. Yeah, if we look at this as a triangle, actually, base times height, this is equal to 1. So we're going to subtract 1 from our 8 points. So this area here we said it was about 8.75. About 8.75. This is equal to 1. So subtracting that area, we're going to get this is going to be 7.75. And so we have another value of our graph of g. 6, 7.75. Our graph has of g, look, our graph of g has grown from 0 to 4 to 6 to 8, and now it's fallen to 7. Because our graph was growing when we were accumulating positive area, and our graph is shrinking as we accumulate negative area. So this is what the accumulation function shows you. It shows you how the graph is growing or shrinking, how the graph is accumulating growth, if it's increasing, or decreasing if it's negative. Last one, g of 8, from 0 to 8, the integral from 0 to 8 of f of t. Again, we have some more negative area here to accumulate. We got all of this 8 here to here. This is, again, a triangle, so we can use our ingenuity. 1, 2, 3, 4. Base of 4, height of 2. Let's see. 1/2 of base times height. This is going to be a total area of 4. 1, 2, 3, 4. Yes, total area of 4 in this lower area. So again, we're subtracting. We gained 8.75 from this part. We've lost 4 from this negative part. Together, total, this is equal to 4.75. Ayala, welcome back. How's your arm? Ayala also got his shot, everyone. Round of applause for Ayala. Getting our jabs. Good for now, yeah. We'll see how you... Oh, well, good, good. Very good, Ayala. It's good to have a buddy. Buddy system. Vaccine buddy system, very important. I'm glad we are all there for each other. It's a very small needle, very small needle. Actually, when I got my first shot, I didn't feel the needle go in at all. I don't know. Really good, well-practiced nurse. It was their, I don't know, 7,000th jab or something. So I'm sure they're well rehearsed at it. So again, good job, Ayala. Everyone else, you're next. Get your jabs, everybody. So let's talk about this accumulation function again. So we are growing g of x. We are growing it from 0 to x. We are adding up, right? This integral here means we're adding up the area under the curve, starting at 0 to some value, and we tested it for different values. What if the integral went to 0? Well, if it starts at 0, from 0 to 0, we know that's nothing. That's 0. And then our graph grew as we went to number 2, right? Our graph grew. We accumulated about approximately 6.75. We said this is about 6.75 in this area underneath from 0 to 2. We grew that much. So our graph of G grew to 6.75. I looked at 1, 2. If we look at just 1, it's just 1, 2, 3, 4. The accumulated area from 0 to 1 is this area here, which is just 4 squares. So we have 1 comma 4. So we're growing our graph. We get to 4. This is the maximum value our graph is going to reach. We have accumulated all of the positive area of the graph. This is at 4. This is where our graph of G is going to be a maximum. Because after 4, right, we get from 0, 4, 6, 8. After 4, our graph starts to decrease because we're in the negative area now. We are shrinking the graph. 8 to 7 to 4. So we are decreasing on this area, and we've increased from 0 to 8.75 on this graph, right? So this is approximately the values of the integrals here, of the G accumulation function. We are growing our function, adding up the amount of area under this curve. And with this idea, we can think about what the graph of G might look like. We know it's going to increase over here. It's going to grow. It's going to grow. It's going to grow slower, and then it's going to eventually peak, right? We know what that looks like, what the peak looks like. When we have a graph that's growing and peaking, it's growing less and less. That looks like a downward curve. It looks like a concave down, like a upside down parabola, right? Concave down parabola. Peaks at 4, and then continues downward after 4 to 8, right? So it's going to go from 0 up to 4, maximize at 4, and then downward there, right? Downward there. So it may look a little bit different. We have some details here we'll talk about, but we basically know the graph is growing until 4, peaks at 4, and then starts to decrease, and that's the graph of G. Graph of G, what the graph of G looks like. So we estimated those. Part B, find the largest open interval on which G is increasing and the largest open interval on which G is decreasing. So we know how to do that now. From 0 to 4, G increases. From 0 to 4, right? From 0 to 4. We can do an open interval, doesn't really matter. But the section from 0 to 4, G is increasing because we are growing the graph of G. We're adding to our integral. We're adding to our area. From 4 to 8, G decreases. From 4 to 8 because all of the area under the curve is negative. Right? All the area under this graph is negative. Our graph shrinks. Our graph shrinks. Right? We're growing here, shrinking here. So the graph of G is increasing from 0 to 4, decreasing from 4 to 8. Question C, identify any extrema or extrema of G. Extrema are the things that are the maximums, minimums, maybe any kind of, you have asymptotes, like vertical asymptotes, breaks, holes, right? Various important parts. Most typically, maximums and minimums. And we know there is an extrema at 4. We know that 4 is where the graph stops increasing and starts decreasing. Okay? Our graph is growing over here, graph is shrinking over here. So if we change from growing to shrinking, what kind of extrema are we going to have? G has a maximum at x equals 4. Because we know that the graph has grown up until 4. We're increasing until 4. And after 4, we start to decrease. So if we go from growing to shrinking, positive to negative, right? Positive graph over here, positive area over here, negative area over here, positive, negative, we know that is going to be a maximum. So let's now take this information and try to sketch a rough graph of what G looks like. Zoom out a little more. Sketch a rough graph of what G looks like, this accumulation function, what it looks like. So let's go here. I know I only have positive values, so this is going to be G. G of X. I have 1, 2, 3, 4, 5, 6, 7, 8. And my maximum of my G is 8.75. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It goes up to 9. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? So we're going to sketch out a rough graph of what G looks like. We know the graph starts at 0, 0. So these are G values. So my first dot is on 0, 0. My graph starts at 0. My graph starts with no value. At 1, we calculated the graph goes to 4. So at 1, the graph is going to be up to 4. So that's pretty good. 1 to 4, I have a point there. 1, 4, right? 1 comma 4. 2, we added up all the area under the curve from 0 to 2. We said that was about 6.75. So 2 is about 6.75, maybe like here-ish. We don't have one for 3. 4, we have 4 is 8.75. So here's my maximum. 4, 8.75, right about there. 6, we have at 7.75. So 6, we shrunk a little bit. 7.75 at 6. Let me try to get this accurately there. Shrinking at 7.75. And then at 8, we have it at 4.75. So 8, we go all the way down to 4.75, right about there. And so we see our graph is going to grow and then shrink. Grow and then shrink. We can sketch a rough curve here. That's going to go straight. And then we kind of have some curves, maximum. And then we curve down like that. Something like this, right? We curve up here till we reach a maximum. Oh, stop that. Curve up here. Goodness gracious. Curve up here until we reach a maximum, and then we curve sort of like more curvy down there. And that's roughly what the graph of G will look like. Right, here's our maximum at 4. Our maximum here at 4. 4, 8.75, and then roughly going like this. Questions about that? What questions do we have? If your question is, how do I know how these numbers look? That's a great question. The question is, how do I do this? Let me know that. Let me know what your question is. Why is this number that way? Why is that this way? Let me know what questions you have. Or if it's all clear and you want to try 86, I know that too. Are we good, everybody, or are we lost? I'm getting nothing. I see a lot of blank squares. Anyone have questions about this process, what we did? Okay, that's, I mean, profound question, Paraiso. The answer is, what else would it equal? You know? All right, so if we're good with this, let me show you a couple little details. Let me show you a couple little details of this graph that we know. So look at what we have found here. Basically, let me remind you of what we found. G here, this graph of G, and this graph of F, right? Basically, this graph of F of T is the derivative of G. This graph of F here is a derivative graph. Because if G is the integral, right? Let me show you this again. If G is the integral, right? G is the integral of F. Then if I take this integral and move it over here, right? If I undo it, then if I do the derivative of G of X equals F. Right? So if I reverse it, G is basically F prime. No, I'm sorry, I had that backwards. F is basically G prime. So F of T is G prime. So this F graph is a derivative graph. So we know the derivative graph. Basically, we're taking the derivative graph and going backwards. Which we've done before, but we're doing it more organized. We have values of these equations, right? We know data now. We can look at the area under the curve. That area gives us the value of the points. So if we're taking this derivative and we're thinking, okay, what did the original equation look like? We have some clues we know about. We have some ways to think about what we know. This part of the function from 0 to 1 right here, where it's a straight line, right? Where the derivative is a straight line. If we undo that, this part right here is going to be linear. That little section from 0 to 1, we know that's going to be a straight line, because if you undo a derivative, right? If your derivative is flat, the antiderivative, the thing that made it, was a line. If the slope is positive, the slope of this is 4, right? The slope of this line is 4, so our slope goes from 0 to 4, right? You see there's my slope. Linear section of the graph. The section of the graph here, from this curve to this curve, is curved downward, right? It's curved like this. So that's going to be a curved section right here. Curved section here, right? Because it's decreasing by different amounts, right? It's going to be a curved section there. Might actually, well, anyway, it's going to be curved like that. This, I'm going to do this in red, I guess. This section of the graph here is linear. And if we undo a linear section, this graph here is going to be a parabola. Parabolic. It's an x squared part of the graph. It's curved like an x squared equation. Because if you do an antiderivative of a line with an x, you get another x, which becomes x squared. So you see this hierarchy of graphs, right? Polynomial, sort of like hierarchy, or how do you want to call it? Hierarchy? Hierarchy. So if you have a line, if you do an integral of the line, you get a flat line becomes a linear equation, right? and going up this way is a derivative. So line, a flat line gives you a linear equation. Linear equation gives you a parabola here, x squared, right? X squared. This is x, this is constant. If you do it again, you get a curve, x cubed. And if you do it again, you get an x to the fourth power, 1, 2, 3, 4, right? X to the fourth power. And if you integrate, if you do derivatives, you get up and down this chain. Right? So if you see a flat line, you know the integral of that's going to be a linear equation. If you have a linear equation, you do the derivative, you're going to get a flat line. If you have a linear equation, you do an integral, you're going to get an x squared. If you have an x squared, you do a derivative, you're going to get a linear equation. And so this hierarchy you have of polynomials, right, goes up and down this chain as you do integrals and derivatives. And that just tells us kind of the shape of things. And so we can see here, this green section was a flat line. The integral of that's going to be a linear equation. Flat line creates a line. Constant becomes a line, right? The linear equation becomes a parabolic equation. Right? Line becomes quadratic because when you add an x, you add a now, you have x squared. This equation, it gets more complicated with things like inverses and various other things, right? We have this kind of chain going up and down of things. Right? We have also, you can think of like trig hierarchy, right? You have sine and cosine. They kind of go back and forth together, right? Sometimes there's a negative involved, right? With sine and cosine. It loops round and round and round, right? And then cosine, when you do the derivative, becomes a sine. And you do the integral of the sine becomes a cosine. So it's kind of, it goes back and forth around in both directions. Loops around like this. Cosine becomes a sine becomes a cosine. Swapping negatives back and forth. We have maybe the derivative of 1 over x. If you do the derivative of 1 over x, you get ln of x. You do the derivative, right? And if you do the integral of ln, you get a 1 over x. And so this is a kind of loop that they make here. Actually, I think it's the other way around. Integral here and derivative here. Do the integral of 1 over x, the derivative of ln, you get 1 over x. So it's kind of a loop here with ln and 1 over x, right? So there's these little like groupings that you get in integrals and derivatives where you have these connections together with all this stuff. So this is what you need to become intimately familiar with. Polynomial hierarchy, trig hierarchy, ln, integral derivatives of natural logs. We know the hierarchy of e to the x. E to the x just loops on itself. Integrals and derivatives doesn't matter. E to the x, the pattern for e to the x is it becomes e to the x again. It just kind of, it's the only thing in all of nature that is its own derivative and its own integral. So that's the kind of stuff we need to be aware of and conscious of when we're looking at these graphs and thinking about how all this stuff connects together. We've got like 9 minutes left. Not enough time. All right, let's look at number 68. I'm going to do a little bit of this one over here. Just sort of quickly. 68. The graph is, I don't want to erase that. It's here. So here's the graph for 68. This is f of t. So I want to estimate g of 0, g of 2, 4, 6, and 8 again. Same kind of idea. G of 0. Integral from 0 to x, 0 to 2. So we want to find this area here. This area here. Well, again, we have a triangle. This is a linear graph. So 1/2 base times height. Height looks like it's going to be 4. 1/2 of 2 is 2, so this looks like it's going to be a 4. So we have, oops, sorry. That's for 2. For 0, it's 0. 0, 0. G of 2 is 4, so we have 2 comma 4. 4, G of 4. 0 to 4 goes here. This is another triangle. We try to find the area under this triangle curve. Again, 1/2 base times height. Base is 4, height is 4. 2 times 4 is going to be 8. Oh, I'm sorry. This should be negative 4, shouldn't it? 2 comma negative 4. 4 comma negative 8. Because we're going below the axis. Our graph here is accumulating negative areas. So we're decreasing from here to here. We've decreased from here to here. Now this is all decreasing here. Area going negative. So our graph of G is starting off at 0, and then going down until 4, down, decreasing, decreasing, decreasing until 4, right? Decreasing, 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 decreasing until 4. Once it hits 4, now we're going to have some positive area here. So now my graph is going to start to increase, but it's still in the negative area until it has grown enough to pass and become positive. So we have to overcome this negative 8 deficit that we've kind of earned in this area over here. Negative 8 deficit we've earned. So G of 6, let's go to 6 here. This area here we have, let's see, 1, 2, 3, 4. Sort of a triangle here. 1/2 base times height is going to be 2. Maybe this area is 2 and this is 4, so that's about a 6, right? So it's grown by 6, but it also has all this negative 8. So negative 8 plus 6, this is going to be 2 and this is 4. So 2 to 4 is 6. So negative 8 plus 6 is negative 2. 6 comma negative 2. Right, and G of 8. What is that going to be? Well, if that's 4, if that area was 6, the area in the whole thing is going to be 12. So negative 8 plus 12 is positive 4. So 8 comma positive 4. So we crossed over. We had enough positive area to overcome our negative area. Now we're in the positive territory. We are still in this section from 4 to 8. Our graph is increasing. Our G graph is increasing. It only becomes positive, though, once we have overcome the deficit that we had before and overcome this negative 8 deficit we had. So we have these coordinates: 0, 0, 2, negative 4, 4, negative 8, 6, negative 2, 8, negative 8, comma 4. And we can use that to graph the graph of G and identify some extrema, right? And clearly 4 is a place of change. X equals 4 is a which one? Maximum or minimum is x of 4 going to be? Think about what's happening on the graph. This part is decreasing. And then we change to increasing. Say it for everybody, Lizette. Very good. Yes, it is a minimum, right? Because our graph is decreasing. It was negative, changed from negative to positive. And as we remember our hand curves, right? If the graph is going from negative to 0 to positive, that makes a minimum from negative to positive. So use what you know about that. Try those equations out. I'm going to add a couple more here that I want you to try. Oh, right. So I'm going to add a few more equations to your assignment because we got 3 minutes left. It's going to be, let me open up a couple other questions here. It's going to be not those. It's going to be the next page. Let me see if I can get the next page open here. Hold on, everybody. Questions I'm going to add to your assignment are going to be here. So we had 67 and 68. I want you to try those. I would like you to try 87. 87. Sketch approximate graph of g, right? So now again, this is our derivative graph. What does the integral graph look like? And then 89, 90, 91, and 92. 89, 90, 91, 92. So they're asking, in these questions, they're asking you basically to do some integrals. So let's look at 89 quickly. Water flows from a storage tank at a rate of this amount of liters per minute. Find the amount of water, right? So this is this equation here represents the rate in liters per minute. So this is like a flow rate. You can imagine what's happening here. It's 500 minus 5t. The rate is decreasing. So it's flowing very quickly and then it slows down to a trickle, right? Find the amount of water. So amount from a rate is an integral that flows out of the tank during the first 18 minutes. So we're going to integrate from 0 to 18 this equation here. Now, this is our rate. We do the integral of that rate. It will tell us how much water has flown out of the tank in those 18 minutes. And the same with these other questions. But that's an accumulation function. We're figuring out how much we have gained or how much we have lost, right? What's the rate, right? Again, same thing here. We have an oil leak at this equation here. We're figuring out how much is lost from 1 to 4 p.m. So that's going to be an integral from, well, let's see, starting at 1 o'clock till 4 o'clock. Is it going to be an integral from 1 to 4? No, it's going to be an integral from, this starts at 0 hours, and here is 3 hours have passed. So from 0 to 3 is what this integral is going to be, right? Because we're starting at 1 p.m. 1 p.m. is like the 0th hour. 1 p.m. is our starting hour. So that's like 0 hours to 3 hours. And again, from 3 hours to 4, 5, 6, 7 hours is 6, right? And then answer question number C. So you're using your accumulation, using your integral to determine amounts of things. So that's going to be your assignment when we check in again on Thursday. Tomorrow I will have, and then 91 and 92 also. Tomorrow we will have a little review session for practicing the AP test. Come by on tomorrow during our study session hours. Other than that, good luck.